well, let's get going. Again, welcome to Dr. Data Science, our monthly series, covering the story of a real-world data science project. And as you know, we appear here the third Wednesday of each month. So you can do the math. Next session will be on June 16th. So this chapter, we're going to be talking about the modeling phase, and actually a particular style of modeling that I'm not sure I could say we invented it, but it's certainly something that we sort of arrived at sort of for business reasons, and also because of the need for sort of highly accurate models. Anyway, we'll get to that in a second. But let me remind you about the story so far. If you've tuned in before, or you can go and look at our YouTube channel that we just posted in the chat there to find out what we've been talking about so far. But just a brief summary. We're talking about a project from high-tech manufacturing. We think the techniques are pretty broadly applicable of feature generation and dimensionality reduction and modeling and model deployment and architecture and so on. But this particular project is about identifying essentially anomalous wafers. Wafers are these big plates of silicon chips, dice, I guess is the plural, and they get produced in a fabrication plant, a fab, over a weeks-long process and multiple layers of silicon and laser beams pointing at them and etching and heating and cooling and all sorts of processes that are all mapped with many, many different sensors and then tested at the end with a variety of different tests. And these wafer maps essentially are a sort of visual way of looking at how did the wafer do during the manufacturing process. And in this particular screenshot that we see here, anything that looks sort of orange like that is a sign that something has gone wrong. So those that are mostly blue is a sign that, yep, these dies are passing the test. But some of them may have these patterns. And some patterns are of particular interest. Literally, the physical formation of the pattern indicates that there's something in the manufacturing process going wrong, maybe a leak or an area of high temperature. And we want to identify those and figure out what's going on. So you'll remember in the previous session that with Nico, we talked about using clustering techniques to identify those patterns. So from this thousands of wafers, use clustering. We ended up using a form of clustering or dimensionality reduction, really called self-organizing maps, where we could identify particular patterns of interest, like a ring pattern or a blob or a scratch or something like that. So now that we've identified those clusters, the pretty crude approximations to the patterns of interest, we want to actually build a model to identify those in the future. Why do we need a model? Why don't we just use the clusters? Well, the point is the clusters are imperfect. They're just an unsupervised suggestion of what's appearing in the data. As you saw with Nico, we spent some time sort of moving things in and out of those clusters and sort of defining new targets. So once we have a target, then we actually want to model that. And that's what Sweta is going to be talking to us about today. So Sweta, welcome to Dr. Data Science. You're a fairly new member of the TIBCO data science team, right?
Yeah, pretty new.
So welcome, and remarkably, you've picked up almost all of the technology and you're familiar with this project now, and you did a great talk yesterday at the Dedicated conference that people may be able to find online. That was about renewables, so you've certainly, in a very short time, done lots of really cool work. I want you to help explain, how did we do this model? We've got these clusters, or we define these target patterns, sort of what happens then to build the models?
Yeah, so I think this is best by show by example. So I'll go ahead and bring up the actual wafer map demo that we're going to be taking a look at. Yeah, so again, what we really want to focus on is how do we actually identify these patterns once we've built these clusters? And what I'm going to show you over here is a single pattern that I was able to construct from the clusters. So I've identified this thing called the heart pattern. And the way we did it, going back, is that again, we have a section over here called the composite wafer map for clusters. So these are, so each one of these really represents a cluster of our wafers, and the composite is an average across all those clusters. So what I want to do is able to pick one or more of these and just try to identify some type of pattern or try to label it as some type of pattern. So what I did is I actually selected this one. I said hey, this kind of looks like a heart. And I just manually entered that name and added it as a new pattern, and we can see that pop up here.
Right.
What's also interesting is that you can, identify one or more clusters that fall into the same category. So it looks like here, 0 and 7, might appear as these like general heart shapes. So
Nice.
we're populating those.
I'm really glad you
pattern.
emphasized that, actually, because that is part of the magic that Nico was talking about last month of how these self-organizing maps, just the proximity of the clusters to each other in this diagram, indicate they might be similar. And so that helps the, well, it's the factory engineer in this case, identify these patterns of interest and label them more comprehensively.
Yeah, so there's also like a spatial representation of the clusters, and it's easier instead of having to go through like 50 or more of them manually.
Right.
Yeah, so what we have right now, again, is an existing heart pattern. And you can see over here that there are 23 wafers in this heart pattern. So that's what I've defined right now. And the next step we're going to go to is using this pattern, training a model on this pattern.
All right.
Yeah, so you can see here that I have selected this heart pattern as our target. And now what I want to be able to do is train a model that can learn this heart pattern. So it's either saying something is a heart or it isn't a heart. And the idea that we want to train a model to do this is essentially we want to use the same model in the future to be able to deploy it on like, future wafer maps that come in that have no such label. So all those that have are like maybe some type of output from the clustering, but there's no label associated with them. And in order to actually like train our model, what I'm actually going to do is run it at this lower classification threshold. And the reason I'm doing this is because what we're interested in is seeing this category over here, which is called, which is essentially the false positives in a confusion matrix. So just at a high level, a confusion matrix is a really good way just to see in this binary situation, like what your model is getting right, and also like what it's getting wrong. And like I mentioned,
those 23 there, those are the ones that it said, according to the model, are hearts. And I guess we can quickly check that, right? And they do actually look like hearts. So that's good.
Yeah. So it looks like, 23 of them were identified to be hearts, and they actually were labeled to be hearts, as we saw before. So, and then there's also like 470 of them, like many more that are just not hearts at all. And, we didn't have to dig through any of that data. We just were looking at these 23 hearts for right now. So what we're actually kind of interested in here is this section over here, which is the false positive section of the matrix. And the reason that we're kind of interested in it is because what this is showing us is anything that the model thinks has the slightest chance or the slightest probability of being a heart. So when we lower this threshold, saying where we're asking, like, give us anything that kind of looks like a heart. And again, that's of interest to us because we want to build our training set. We want to find all these instances of this relatively rare pattern. So now that I've actually found them, what I can do is I can actually select them. And well, that's what I'm going to be doing here. I'm going to select the instances that I think are a heart. And here I've actually selected, it looks like 6 out of the 7. For right now, I wouldn't really classify this as a heart. But I think that these should be hearts, even though they aren't currently labeled as hearts. So what I want to do is actually reverse this labeling. And that's what I'm going to do when I hit this button called add wafers to the target. I think that these wafers should be hearts and should be included in our training set right now.
So you're labeling these for the new training set.
Yeah, I'm adding them to our new training set. And then what I'm going to do again is just, well, if I were to run this model right now, you can see that it just kind of gives you kind of like one of the wafers that we saw before, plus like another one that came in. And I don't think either of these looks like hearts right now.
It's but what I think interesting, Sweta, sorry to interrupt there, but
yeah.
It's kind of interesting because that top one arguably is kind of like, sorry for the traffic outside my office here. It looks like almost like a rotated heart. So it might be that those Bessel functions we were talking a couple of months ago are actually doing a good job of sort of handling rotation. That's sort of arguable, I guess.
Yeah, it's definitely, it's definitely up to, I guess, like the user subjection, whether this is a heart or it isn't. It's nice to see that this like rotation pattern is very similar to what it is here. So if you have just like a wafer on the factory floor that's like rotated red, we can still find that to be somewhat similar to the heart pattern.
That's right.
Yeah, so actually I just ran this at the same threshold and you see that just these 2 wafers once again pop up. What I can do is kind of repeat the same process and just try running at even a lower threshold to again say, like, give us anything that could potentially be a false positive. So I'm really not seeing anything at this point that I think could be a heart. So what I want to do is say, like, I think I found all instances that could possibly be a heart in our data. So I'm just going to, set this back to the normal threshold and just run our model. And then now what we see is that we have 29 patterns of the heart instances that are correctly classified as a heart. And we built our train set, I think it was below in the low 20s before, and then we bumped it up to like around 30. So you can actually just imagine how this would scale on a pattern that, might be is more infrequent or is more frequent on a larger setting. Mm-hmm.
That's really powerful. The thing I like about it is the way that, the machine learning is doing what it does best, which is to, in a very dumb way, just go out and try to identify these things and then sort of offer them up to the intelligent human and say, what do you think? And then the human gets to sort of refine the model. So this interaction between the model and the human engineer is great.
Yeah. Yeah, it's particularly nice to have because, AI can't solve all your tasks. It is important to have human intervention, especially for tasks that are like either high risk or like maybe there's high stakes for them. Yeah. And I just would also mention that it looks like just from these metrics over here that we again have like a pretty nice model that can at least identify this heart pattern. And, in the future, we would probably want to see something where this model is like deployed to, be able to identify heart patterns in new data that is completely unlabeled.
That's great. Just very quickly before you move on, when you hit that run model button there, what's going on in the background?
Yeah, so it's actually running a random forest model. So random forest is a supervised model. It requires the data to be labeled in some sort of way, which is what we've provided it. We provided it data that's either labeled to be a heart or not to be a heart. And the random forest is a great type of model because it can handle like high dimensional data and imbalanced data. And right here, it's working on like a binary type of setting, labeling something as heart or not a heart.
Great. Okay. And then that's running in one of Spotfire's data functions. Is that right? Is it Python or R or?
It's going to be running in a Python data function. Awesome. That's just inbuilt into Spotfire. And you can see that we can constantly refresh that function with updated parameters, which is what we've been doing during this iterative process.
That's great. And I can't help but mention yet another one of the things that you've done in just the first few weeks of joining TIBCO is actually you're publishing some new data functions, right, in the TIBCO community.
Yeah. Mm-hmm. So there is a random forest Python data function that's available in the community right now. And there's a whole bunch more that have been added for like regression or classification tasks, and hopefully some ones that are upcoming in like text and other fields.
Awesome. Great.
Awesome. So if there are no more questions here, I'm gonna go switch back over because we wanted to talk a little bit more about what's actually going on here. Before we go into a little more of the technical depth, it is kind of interesting and important to this project just to give a little bit more background. So this is kind of, I don't want to say it's machine learning like 101, because I think a lot of these terms are commonly like interchanged or used without precise definitions. So it's nice to like be able to categorize them in some type of way. So like, machine learning often has like certain types of problems. And the way I think about it is just like, how is your data, like what format is the data coming in? So learning problems include like supervised learning, what I just mentioned with the random forest, where we're working with data that's labeled in some sort of way. Semi-supervised learning deals with data that's both labeled and unlabeled. Usually it tends to be like the vast majority of your data is unlabeled and you have a small setting that is labeled. And then also unsupervised learning, which is working with unlabeled data. So this is like, a spectrum. It's not like hard categories.
Yeah.
Mm-hmm. And then there's also learning techniques with that. So some of the different types of learning techniques are active learning, online learning, ensemble learning, and transfer learning.
I'm familiar with some of those. Ensemble learning, I assume that's where you have these sort of sets of models, multiple models that are sort of all learning in their different ways, often in fairly dumb ways, but then you sort of aggregate them together. That's what you mean there. And online learning is just sort of like streaming data coming in and the model's rebuilding itself.
Yeah, so it's exactly like how an algorithm decides or how an algorithm is built to learn. So in the online setting, an algorithm like takes one instance, for example, at a time, and then updates or makes some type of decision from just that one instance.
Got it. What's transfer learning? I'm not familiar with that.
Yeah, so transfer learning is when an algorithm is built or learns from one sort of task, and then we use that knowledge to train it or fine tune it on another type of task. So just like an example is that if we have an algorithm that's able to, I guess like identify different types of cars, we might use that same algorithm and either train it or use that exact one to distinguish different types of trucks.
Great. Okay. And active learning, I think you're going to dive into that a little bit, right? Because that's similar to what we're doing here.
Yeah. So active learning is really the main learning topic of today. It's a type of learning technique that relies on human intervention, and specifically like smart human intervention. So now that we kind of gave a background on some of those learning challenges, we also want to just talk about how they're incorporated into this Wafer demo. So there's two main questions that I think are important to ask. It's how can we learn patterns from an entirely unlabeled data set? And this is what we have when we're working with the Wafer demo, right? We're starting off with wafers that are completely unlabeled. And what we did is applied a series of like unsupervised learning techniques, the Fourier-Bessel transform, the singular value decomposition, and then the self-organizing map, in order to get them into some simplified representation, which is the wafer maps we just saw. Yeah.
Great. And then if people want to learn more about those, check out the YouTube channel where we've got previous presentations. Sorry.
Yeah, the previous Dr. Data Science sessions covers a lot of those in depth. And so like once we've actually had those representations, we want to be able to, manually identify patterns. So like name clusters or name multiple clusters, and then find all instances of those patterns. And this is really what we saw today, which is a combination of both supervised learning from the random forest and active learning, which is where we rely on a human to come in and do some of their intervention, or I guess lead that iterative process.
Right.
So I think it's also nice to just go in a little more depth about what active learning actually is. So again, the technical definition is that active learning is just a technique that uses human intervention with AI to optimize solving data-driven tests. And really the issue at hand is that labeling data is very costly and timely in a lot of settings, and probably especially on a manufacturing floor. So what the solution kind of is that we can be smart about how we label our data. So while an algorithm is running, or like before it goes through its next update, we can just choose some set of the data to be labeled. And so AKA choose some set of the data to be sent over to an expert and have them label it. And this could actually help our model just learn overall better, or as good with having all the data labeled.
Got it, understood.
Mm-hmm. So yeah, this is just like on below here, I just wanted to show kind of like more an example of how that actually looks. So we have, so like if we were to say, for example, we have some of our data labeled in a binary setting. So we can say like these blue points over here are things that are not a pattern. And then we can say that these red points are things that are a pattern. And right now, let's say our random forest model is stuck in this kind of decision boundary right here. Or it's not stuck, but after one iteration, it's learned this boundary. So these gray points are all instances where we don't know if they are or are not a pattern. And one of the strategy, which is called like uncertainty sampling, is just that we want to just select points which we are most uncertain about, or which we think can lead to like the highest information gain. And really, those happen to be the points that are closest to this decision boundary. Because depending on whether, if this point were to be labeled blue, for example, this decision boundary can be moved over here. And that's, that then results in a complete separation of the points that we do know to be labeled. And vice versa, if this was to be red, it can move over here.
Got it, I see. So crudely put, in this sort of binary classification, saying, well, where does it sort of come up with a probability of 0.5 or around there? And let's focus on those ones, because presumably it's not so valuable looking at the endpoints, the zeros and the ones, but in the middle is maybe where we need a human to help out.
Yeah, in a binary setting, when you're looking at like things that are labeled with a 0.5 probability, it's the exact split of either being a pattern or not a pattern. So that's where most of the uncertainty is.
Got it.
Okay. And then we want to talk about also how active learning is applied in the wafer map demo. So before we go into like the actual active learning component, it's a little bit important or nice to like reestablish what we want to do in the Wafer map demo. So again, we want to find examples of our patterns of interest. And that's really what we're trying to do. And that's why we're bringing in active learning, or like a variation of it, as we'll see. And there's two questions that are kind of important that we want to ask in general for active learning is just when should an expert or a human intervene? And also, what should that expert do? So in the case where we're talking about when should an expert intervene, well, there's like kind of two different situations, and it also really depends on the type of algorithm that you're working with. So in the pooling scenario, you often have an algorithm that kind of labels all of the, or makes predictions on all of the unlabeled data, and then it gives some subset of it to the human. And there's also the streaming scenario where you take in one instance at a time, and then either an algorithm or a human decides to move on with it or not.
So in the Wafer map scenario, right, I think that the most common use case there, I guess, would be the pooling, right? Because you're generally saying to the engineer, if you're just looking at wafers coming in off the lot, they're probably a little bit overwhelming. But instead focus on sort of historical examples, where historical might be up until an hour ago, but it's not streaming. You've got a static set and you're researching those, you're doing that sort of clustering investigation. So is that like what you mean by the pooling scenario?
Yeah, it's a variation of the pooling because we're running it on all of our data at hand collectively, and then making a decision on some subset of it to look at.
I see.
So yeah, so that's like, that happens to do like when should an expert intervene, and that's why we call it a variation of the pooling. And then it comes to account like what should the expert actually do. Right. And again, this also goes hand in hand with what type of algorithm you're using. So if you're going about like a strategy of like, I don't know, you're just working with one model, and you could go about with uncertainty sampling, which is again just looking at that 0.5 threshold where we're most uncertain. There's also like there's multiple strategies. I just thought I'd mention one more. Yeah. There's this thing called like query by committee. If you're working with multiple classifiers, you want to be able to see like where those classifiers disagree, or like if you're looking on one classifier and just running it on a subset of data, you can see where it disagrees like iteratively.
I see.
And in the Wafer map demo, I think we do something that's a little more untraditional. What we're actually doing is, and there's no strict name for it. What we're actually doing is just being able to have a user come in, lower their cutoff, and then query the false positive section of the confusion matrix. So it still requires human intervention, but it goes back to the purpose of finding examples of patterns of interest, or finding as many examples as we can of this pattern of interest.
So is it a sort of variant of, because it seems roughly like uncertainty sampling to me. You're looking at these different probabilities, you're getting down to a subset. And
yeah, I would say it's a variation of active learning for sure. So the thing is with uncertainty sampling, I guess it assumes that all the data is properly labeled to some degree, but really the fact is that when we've labeled things to be patterns or not patterns, we're quite unsure about the things that are not patterns. Right. So that's why we can classify it as a variant.
Interesting. Okay. Yeah, that's great. It's funny because, you know, the team, I think, wasn't really super well versed in these distinctions that you've laid out here of these different techniques for doing the learning. We sort of arrived at this method really at the behest of the client in this case, who was insisting really that they wanted to automate as much of this process as possible, because it's very important for them to catch these things and catch them early, and there's just too many things to monitor. And you're not just looking at lots of wafers, but of course these like really complex wafer maps and all that data. I mean, it's just a huge quantity of data. There's just no way for a human to sort of grok that. But on the other hand, they insisted the human has to be involved, right? We don't want to just have some sort of lights out method. I mean, they can't really. I mean, even if your clusters were perfect and they were really good at identifying just these sort of anomalous patterns and separating them out very carefully, the human needs to decide which ones are actually interesting, right? I mean, a heart and a scratch might both be interesting at different points in the manufacturing process. So it's sort of interesting to me that because of that requirement, we sort of backed into what is roughly, as you say, active learning without even knowing what active learning was.
Yeah, and I think, yeah, it just ties into like what is our main interest here And again, it's identifying those patterns and finding as many of them as we can.
Right, right. Well, great, Sweta. Talking of that client, actually, one of the things we discussed as we were sort of refining this method was this notion of human-powered AI, which is maybe a slightly grandiose term, but I like it. The sponsor that we were working with here, the company, the high-tech manufacturing client, said there's a little bit of an oxymoron, of course, in a way. Like, what does it mean to have human-powered artificial intelligence? But I sort of like the paradoxical nature of the label. And, you know, I think it relates even to some discussions around sort of ethics and AI, right? That this ability to have machine learning do the thing that it's good at, which is to deal with large quantities of data in a sort of automated way, but not just to have the human involved in that process, but actually have the AI help the human do their job to scrutinize the cases that are the most interesting ones, the ones that are close to that boundary in a sense.
Mm-hmm. Yeah, it's really about being smart about how you bring a human into this setting. It's being both smart about how they're interacting with the data, and also, of course, for like safety and ethics considerations, it's always nice to have an extra human eye on this type of process.
That's right. Well, Sweta, thank you so much for presenting that. Super clear and a good demo as well. And it actually leads us into our next episode of Dr. Data Science, where we talk about model deployment. Definitely a hot topic in the last really year or two, I think, as attention in the industry and in the market has gone away from what's the best algorithm and how do you empower the data scientists with different tools, and more to how does the data scientist interact upstream with the data engineers and downstream with DevOps to get these models into production. So, you know, you pointed out, Sweta, that the models that we're creating here, the random forests, are really good because they're non-linear, they can deal with wide data, they can cope with data that's a little unbalanced. But another random forest, the reason why we chose those versus some other models that we could have chosen is that they're fairly easy to deploy. They're fairly compact, not very compact like a regression or something, but they're fairly easy to deploy. So that's going to be something that we talk about in our next session, is actually how do we operationalize all of this stuff that we've shown in the last few sessions in terms of the data transformation. So that's one that I'm particularly excited about. I encourage everybody to tune into that. Thanks again, Sweta, for your demonstration and for your clear exposition of active learning and these different techniques. And we'll see everybody next month.
Thank you.
Bye-bye.